Hey everyone! We're nearing the end of things in physics to make a rotational counterpart to, so in this video I'm going to show you possibly one of the most fun ones, and one of my favorite concepts in all of physics, angular momentum. Recall that with regular momentum, given by mass times velocity of an object, the big idea surrounding it is conservation of total momentum. With any objects within the purview of a situation, there's a linear momentum attached to each of them in each direction, x, y, and z. How each of these momenta add up give you the total linear momentum of a system, which is a conserved quantity. Even after an interaction between two objects, such as two billiard balls colliding, the total momentum of the system is going to be shared between all of the balls after collision. The only situation in which you will not have conservation of linear momentum is one in which a net external force acts on one of the objects. This is usually done by an object not part of the system, such as gravity from Earth, friction, or maybe somebody's cat jumping on the table and ruining your experiment. The rotational counterpart to linear momentum, angular momentum, behaves really similarly. It too must be conserved before and after an interaction, which in this case, we're looking at angular momentum as capital L, and it's not conserved if an external net torque, which is the rotational counterpart to an external net force, acts on the system. What's slightly different, though, is the quantities that affect it, and the almost magical things you can pull off with it. To give you a look at how this works up front, I'm going to do a classic demonstration of angular momentum. But first, let's have a guess at what affects angular momentum. Remember that the running trend with rotational counterparts is that we simply swap the linear quantity out for the rotational one. If that's the case, then let's start with regular momentum. We've got linear momentum equaling inertia times velocity, or mass times velocity. Then if we're just swapping out terms to see what happens, then angular momentum, represented by L, is going to equal the rotational inertia times the angular velocity, or I times omega. So if that's our framework, let's see what happens if we test it out. If we hypothesize that the angular momentum is indeed a conserved quantity, meaning it's held constant, then the rotational inertia and the angular velocity are linked together, both directly proportional to a constant amount L. This means that if I can find a way to change my rotational inertia internally within a system by, let's say, decreasing it, that means in order to keep L constant, the angular velocity is going to have to increase to compensate for my now lower inertia. In this video, I'm sitting on a stool that rotates and minimizes the external torque from friction as much as possible. I'm going to hold out two 10-pound weights with each arm extended as I give myself a bit of a whirl. At this point, my rotational inertia could be thought of as my body rotating about its center, which let's say is a cylinder, both of my arms extended, which are rods rotated about one end, and two 10-pound weights at the end of each arm, which can be thought as point masses. This all adds up to a fairly sizable amount of inertia to start with. I then bring my arms and the weights down to my sides, and whoa! That feels a lot weirder in person than it looks here. Even then, hopefully you saw how much angular velocity I gained from doing that. Bringing my arms down brought my rotational inertia down to basically just one slightly heavier cylinder, so angular velocity had to compensate by increasing drastically. Depending on how many times you do this demo, you may need some Dramamine. So we can say that angular momentum for a solid object rotating about some axis is L equals I omega. That is kind of a macroscopic view of what's happening though, so let's take a look at a single particle's angular momentum. Generally, for any point P in space, a particle is going to have an angular momentum about that point if 1. It has mass, 2. It's moving with some velocity v about that point, 3. It has some distance r away from point P, which is a vector, and 4, its distance has a component r perpendicular that's perpendicular to the velocity v. This gives us a general formula for a point mass's angular momentum, in the form of L equals mvr times sine of theta. Or in other terms, you could express it as m times the cross product of v with r. This expression for angular momentum is especially helpful for systems with only one point mass. Planetary motion, for example, is dominated by this relationship, where the star that's orbiting is the point P and the planet is the point mass. Kepler's third law states that for any satellite in an elliptical orbit, its velocity increases as it gets closer to the planet it orbits, and vice versa. This is due in part to the need for the angular momentum of the satellite about the planet it's orbiting, point P, to stay conserved. So as it approaches the apoapsis of its orbit, which is the farthest point away from the planet, the distance r has increased, so its velocity v must decrease to compensate. Really, it's no different from someone holding out weights on a spinning stool. Now, angular momentum is a vector quantity, so it does have a direction. Rotational inertia is a scalar quantity, so the direction is inherited from angular velocity if you're looking at the first formula we covered. In other terms, it inherits its direction from the cross product of velocity with the distance away from the axis of rotation. Cross product means right-hand rule. In either case, we can use it in two ways. If you're using L equals I times omega, you make a thumbs up with your right hand so that your thumb aligns with the axis of rotation. Then you rotate your hand so that your fingers curl in the direction of the object that's rotating. Once you've done this, your thumb points in the direction of the angular momentum. If you're using L equals mv cross r, you do the typical right-hand rule, where your index finger points in the direction of velocity, and your palm or your middle finger points in the direction of r. Once you've got this lined up, your thumb points in the direction of the angular momentum. In any case, angular momentum can just as well be described as clockwise or counterclockwise. The official direction of angular momentum can lead to the same frustration that may come with visualizing the direction of torque. So I'm going to show you something that may help put your mind at ease. Imagine that the angular momentum vector is the axle running through a spinning wheel, like on this gyroscope here. Unlike the actual axle that's there, however, the angular momentum axle has magical properties. If a wheel has one, the angular momentum axle will not want to budge. Normally, this gyroscope will just fall over. This axle isn't magical enough, so let's give it an angular momentum axle. Once the wheel's given a good spin, now the axle that's produced keeps it perfectly steady on its edge. The magical axle that's been given to it wants to keep its direction there, and it will completely resist gravity's feeble attempts to change its direction. We can upscale this to have an even cooler effect. This bike wheel has been given a very heavy spin thanks to a motorized spinner upper that was off screen. And look at that! Normally this wheel would just flop right down when suspended by one end of its regular axle, but this one just seems to defy all gravity and logic. It's like magic, but it's not. It's physics. And by the way, you might be wondering why in this scenario, the bike wheel and its angular momentum axle is rotating about the rope. In this scenario, believe it or not, angular momentum is technically not a conserved quantity. Gravity is acting as an external net torque on the system, as shown in this diagram here. Remember that external torques cause changes in an object's angular momentum. That's the whole thing we said we wanted to avoid. But that's what's happening here. The torque applied by gravity is continuously causing our angular momentum axle to change in the direction of torque. And although we want to avoid unnecessary torques for momentum conservation, that idea does have its uses. Spacecraft, for instance, can use the reverse of this, changing angular momentum to apply imaginary torques in order to reorient themselves without using any fuel. They do this with devices called control moment gyroscopes, or reaction wheels. If you're interested, you can read more about them in the description. On a slightly related note, I'd like to end this video with one more cool demonstration of conservation of momentum, this time having to do with direction. Imagine first that a wheel in a system starts out with clockwise angular momentum. If the wheel were to suddenly be flipped so that its angular momentum was now counterclockwise, physics has to do something in order to keep angular momentum conserved. To demonstrate this, I'm going to stand on a rotating platform with that cool bike wheel from before. When I start out holding it horizontally, the wheel has a clockwise angular momentum, or negative L, based on the right-hand rule. Now, when I flip the wheel over, its angular momentum is going to suddenly change to counterclockwise, or positive L. Since angular momentum of this whole system needs to be conserved, a torque is applied to me from within the system to rotate me clockwise until I have an angular momentum of negative 2L. This keeps the total angular momentum of the whole system conserved, and nature is finally happy again. Well, I hope this video was informative, and it gave you an appreciation of some of the cool features involved with angular momentum. It really is one of the best concepts in all of physics. Please feel free to leave any questions in the comments if you have them, and I hope you have a great day. Peace.